It looks like we're up and running, full screen, so I can see what I'm doing. So it's nice to see what you're doing. In this video, I'm going to do some problems that I wish I'd been doing during the other parts of my teaching career, but didn't think of it until just now. I'm really thinking about a kind of a classic algebra problem. The answer to a quadratic, what quadratic did it come from? And the typical kind of textbook method is the, conjugate. And I never really liked that. So I always thought about different ways of doing it. And I think in another video, algebraic shortcuts, I've done this problem in previous videos. But as I was thinking about it, it seemed to me that we spend a lot of time trying to go from A to B and B to A in math, evaluating functions and then solving them for a given value. And this problem, if we have the answer, well, generally speaking, it comes from completing the square to get there. And so why don't we just do the inverse order? Got a feeling that it's probably good for the brain to develop those skills. And in my class, I don't ask students to write down everything. I'd rather see their thought process. And for instance, if I'm going to solve just a very simple equation, 5x cubed minus 2 equals 9, I want to see 11, I want to see 11 fifths, and I want to see the cube root of 11 fifths. Anything more written by my students actually gets in the way of my correcting the problem. Because we're trying to get a disciplined thought process based on the inverse order of operations. When we in other videos, I think I've talked about order of operations, and it's basically, in my estimation, we do the harder operations first and then the easier ones. So when we're solving, we get rid of the easiest operation, the next easiest operation, and then the hardest one to get our answers. So why can't we apply the inverse thought process to a problem like this? And the answer is we can. I'm not saying that there isn't a lot of good algebra that comes from solving this using, some binomial squaring where x minus 5, we can think of x minus 5 as a, and then we've got ourselves an a plus b, a minus b situation. Good algebra that comes from that. We can see the completing the square, but I think it's much better to do the following. And let me write this a little bit differently because I like to line up my equal signs. So let's put the 5 plus minus 3i on this side of the equation. And so what would you do? You would subtract 5. That would leave plus minus 3i. You still get your binomial squaring. X squared minus 10x plus 25. And if we square the left side, we do need to square the right side. And that gets you 9i squared, which is negative 9. And x squared minus 10x, negative 9 to the other side is 34. And we've got our answer using inverse operations. So why don't we apply that to all the equations we solve? Now, I'm sure there are some hidden situations that will materialize as I unfold this process in my class next semester, but I'll wait and see what those are and address them. So right now, you can pause the video and try to figure out what equation this answer came from. I guess we're playing Jeopardy, huh? Something like that. All right, so repetition's my friend, so I put some problems on the board. Now I know to leave some space over here until I get to the last board, and then I did enough problems that I said, well, let's reverse the order. Maybe I can do that right here, right now. Let's set x equal right there. So how would we get 0 on this side? Which I guess is finding some roots here. So I think I'd add 2. I think I would do the inverse of ln right now, which is e to the. And then I would multiply by 5. And then I would subtract 3. And if I set this to 0, I think I can see it materialize. Add 3. Divide by 5. E to the becomes ln. I'm just going to save some writing at this stage. And plus 2 becomes minus 2. Okay, that's a function. And if I want to solve that for 0, I think we're talking about a to b and b to a. All right, so let's put this on this side. 7 plus square root plus minus the square root of 3/2. Geez, I got a feeling that we got another quadratic here. All right, so what function did it come from? Well, you pause the video and you try to find out. I'm going to subtract 7. I am going to square that to get rid of the square root. Yeah, and if I square that, I've got what's inside. I think I'll move the 2. And then I think I'll subtract the 3. Looks like we found the roots. Yeah, then if I want to find out if I get that answer, of course, I use inverse operations. Add 3. Divide by 2, take a plus minus square root, add 7. Boom. I think I'm training the brain to solve using inverse operations. And here I'm doing the inverse of the inverse. I think. I'm not sure what to call it. I'm just starting to think in these terms. So that's the answer to some equation. So it looks like I've got to add 9. I think I've got to divide by 7. I think I got to do the inverse of E, which is ln. And I think I got to multiply by 2. And I guess I got to add 3. And I think that that is solving this equation, finding a root of this equation. Why not? So, could you apply it to trigonometry? A little harder, maybe later in a term after practicing quite a bit with sine and cosine. I talked a little bit about mark on the wall in a cave, addition, subtraction, multiplication, division, powers, roots, e to the x, ln of x, so on and so forth. And we're going to do what when we evaluate? Hard to easy. Always do parentheses first, of course. Okay. So what would it mean if we went from some angle to a ratio of 1/2? Because that's what you do in trig. You basically start learning how to go from an angle to a ratio. And we have the major trig functions of sine and cosine as our initial forays into that topic. So I guess it would have to be, maybe telling a student, okay, this is a sine function whose answer is 1/2. And whether we talk about general solutions or just what a calculator would give you, we'd have to have some work with all of that before doing a problem like this. But let me say that it's a sine function. All right, and the sine function gives you an answer of 1/2. And then maybe I'll say, where else on the unit circle would we get a 1/2? But let's go for a calculated answer. And we know that we have a sine function on this side. The sine of an angle on this side gives us 1/2. I guess I would double. Get 1, and then I guess we would have to subtract 1. The sine of what angle minus 1 equals 0. All right, so where would the sine function equal 1/2? Well, I guess we would have to have our arc. Well, I did trace that pretty darn well. So the arc sine on this side, so we're really looking for arc sine of 1/2. And we know that the sine function goes from 1 to -1, and the calculator is going to go from -pi/2 for answers to pi/2. So there's quite a bit of stuff that has to be learned at this point, but most of my students can tell you what the sine of 2pi/3 is now without any trouble, and it's an Algebra 1 class. We can do it, just got to present it early enough and practice it enough. So some of my students are already looking at this topic, and where on the arc is 1/2? Well, this is halfway up the y-axis. Looks like it's right there. And we've got ourselves a triangle that I hope looks familiar. And I'm hoping folks would say, well, I know that's 30 degrees, so looks like pi/6 is our answer. Nice discussion. And not only took 2 minutes, and then we'd have it again tomorrow and the next day and the next day for a good 20, 30 days. And at the end of those discussions, I think people are usually pretty good with this. That's been my experience. All right, so one more, and then we'll talk about, in general, what we've been talking about. in more specific terms. We'll go to general terms, but let's see if you can pause the video and solve this. I'm just gonna do it underneath here. And just in one line of work, addition of 8 becomes subtraction of 8. All right, we know we're gonna get a 0 here, yeah. Let's put that over here a little bit more. The more I do this, the more I'll leave some spaces here for what I'm sure is gonna show up as a subtraction of 7 last, but let's get there. So I got rid of the addition, inverse operation, multiplication, division. Oh, so now I'm at the major operation in order to get to the argument here and get inside. So what's the inverse of cube rooting, cubing? And then I'm left with division by 5, multiplication by 5, addition of 7, subtraction of 7. And that equation has this for an answer. So basically what have I been doing? I've been taking a function, right, and doing the inverse of that function on this side. So how would we get at it? I'm not sure how to get a more complicated argument at this point. I suppose I should have used sine and cosine or something else, but what would we do? We would subtract 9. We would divide by 7. So it looks like you always get rid of subtraction and addition in these problems first, multiplication, division. Next. And then we did what? Perform the inverse operation of the function. And then we're inside the parentheses. So I've got to add 1. Looks like I've got multiplication by, I guess I got to say 6, huh? I can't really play with that much more than that. So I've got addition of 1 and then, by golly, how do I want to do that? Because I would say 5. I'm not quite sure how to show that other than, you know, sometimes you have AX plus B over C, things like that. So let's go there. Maybe that'll be more helpful. All right, so we got rid of the 9, we got rid of the 7, we got rid of the inverse. Division becomes multiplication, addition becomes subtraction, and multiplication becomes division again. All right, so you just have to kind of follow the thread and develop that kind of inverse process. And so we're going from A to B, B to A. And I wish I had thrown this on the test. I will next semester, because I think it's probably a good thing for the brain to work on. The rest of the problems we solve in high school math, most of them are all about changing sums and differences into products. I hope you know what that's called. Pause the video and think about that for a second. How do you change sums and differences into products? Well, let's get a sum. 2 plus 6. How do you change that into 2 times 1 plus 3? Hope you're saying factoring. A lot of times people don't, use the word and maybe not really understand what you're doing. All you're doing is taking a sum, changing it into a product. All right. And that's how you solve a lot of other problems that you set to those. You set those products, those sums, x squared plus x minus 6, for instance, to 0. And so you write it as x plus 3 times x minus 2 equals 0. And you can solve a lot of equations that way. Solutions -3 and 2, right? And so that's an important skill too. But most of the equations we solve at the high school level, inverse operations, and I'm assuming that probably continues to higher levels of mathematics. All right, so give that some thought, and I'll post this, and I hope it helps somebody. Hope it doesn't hurt anybody. All right, it must be a Hippocratic oath here for mathematicians somewhere. All right, ciao.